Hello, I'm Mohit Chikkadi from the 7th semester of Mechanical Engineering. This is my EL video for the Robust Engineering course under the guidance of Dr. Bharatish sir. The topic that I've chosen is the performance analysis of a cafeteria-serving robot. The robot that we have used for the experiment is I've built this robot. Me and my team have built this robot as a part of our minor project in 7th semester in RV College itself. Hello everyone. Imagine walking into a cafeteria where a robot serves your food. No spills, no delays, just smooth, efficient service. Sounds futuristic, right? Well, with increasing adoption of automation in the food industry, cafeteria serving robots are becoming a reality. These robots to enhance efficiency and minimize human intervention and ensure precise and reliable service. But there's a catch: navigation. A busy cafeteria is no joke. These robots must handle sharp turns and different loads and varying speeds without tipping over or going off course. So, in this study, we dive into how factors like stepper motor speed, weight distribution, and robot speed impact crucial performance metrics: turning, time, tilt angle, and deviation from the expected path. Our goal? To find the perfect setting for smooth, stable, and efficient robot operation in a real world cafeteria environment. Alright, here's the problem. For a robot to work efficiently in a cafeteria, it needs to be fast and accurate. No one wants their lunch delayed or spilled, but three main challenges stand in the way: inconsistent turning, high tilt angles, and deviation from the intended path. Inconsistent turning times, which slow down service and cause inefficiency. High tilt angles, increasing the risk of messy, costly food spills. Deviation from the intended path, leading to navigation errors and potential collisions. To tackle these problems, we have conducted a series of experiments to understand how different control parameters influence the robot's performance. The ultimate goal, you say, to design a robot that's not just smart but also stable, precise, and super efficient. So, what did we test? We focused on three input factors: motor speed, weight distribution, and robot speed. Motor speed in RPM. So, this determines how fast the robot moves and affects its stability to stay balanced during turns. Weight distribution tells us whether the load is evenly distributed, front heavy or rear heavy, and affects the robot's tilt and path. Robot speed in meter per second, this controls how quickly the robot moves forward and its ability to stay on course. And here's what we measure: the turning time, the tilt angle, and the deviation. The turning time in seconds, how long it takes for a robot to complete a turn, let's say a 90-degree turn. Tilt angle in degrees, how much the robot leans, you know, too much and your lunch is on the floor. So this tilt angle is calculated using the accelerometer that is fit on the robot. Deviation in percentage. So how far the robot strays from its intended path. Now let's talk about optimization. So how do we find the best way of setting for these robots? As you can see on the screen, we use three powerful algorithms: the genetic algorithm, driver training based optimization, and ant colony optimization. And this is the data set that we obtained after the experimentation was done. We have trial, the motor speed, the weight distribution, and the robot speed. So we make different combination of these three parameters, and we got different factors, different responses, as in the turning time, the tilt angle, and the deviation. So genetic algorithm optimization. First up, the genetic algorithm inspired by the principle of natural selection and evolution. Think of it as a nature's way of solving problems by evolving better solutions over time. So, how the genetic algorithm works? So, you have initialization, selection, crossover, mutation, and evaluation. So, what we'll do is we'll go ahead and I'll share my screen. We will open the um, Python. Yeah. So we'll open the Python so that we can see the code and we can run it. But before that, in initialization, we start with a group of random select solutions and then selection. Now here, the best solution or the fittest are chosen to continue. Then we do a crossover. So these solutions are mixed together to create a new possibilities, then mutation. So some small random changes are added to keep things diverse. Then evaluation. So we measure how good each solution is using a fitness function. So GA, we will run this code, and once we ran this code, as you can see, the GA generation and the best fitness value, we have run around 100 generations. That is the number of iterations the generation or the evolution worked, and we have also received the results. So the best fit parameters were 54.1 and 0.05 and zero point 0.5, and the best fitness that the GA gave was 85. So with this GA, we found the parameters that significantly improved the robot's performance, reducing the tilt angle and deviation while maintaining fast and stable turns. So most of the optimization happened within the first 40 generation. But like, how do we know that it is the first 40 generation? So what we'll do is we'll take these values, we will copy these values that we have got. We will go back to, we'll open Minitab so that we can, plot this. We will go to a new uh, worksheet and we'll go to graphs. We'll plot a scatter plot. Okay. Before which we have to add the data. We'll come here. We'll add the data that we copied and we will just clean it so that we'll be able to use it. Take out the unnecessary columns. Now we can go to uh, graph, scatter plot, select this one, press OK. Then our generations will be our x-axis. So, and then we press OK. So once that is done, we can see that graph is plotted. Now, within the first 40 generation itself, we got an optimized or a constant value or the constant result. This says that the optimized parameters from the GA directly align with our experimental results, which means better motor speed and proper weight distribution led to improved stability and smoother turns. As in, if the weight was distributed or rear focused or front focused, the turns are not that better. If the weight is balanced, as in the chef or the food is aligned centrally with respect to your robot, then your robot moves or it takes turns much better than it would have done otherwise. That is what we found with this analysis. Next, we have the driver training based optimization, a method inspired by how professional divers refine their techniques through practice and feedback. This algorithm mimics that by learning and improving through iterative adjustment. So how DTBO works? We have initialization, performance feedback, refinement, exploration, and exploitation. So in initialization, we begin with the driver set of solutions, and then we have then in the performance feedback, we have the solutions that are evaluated based on their effectiveness. Then we refine it. So over time, better solution emerge as the algorithm learns what works. And then we have the exploration and exploitation, which is the balancing between trying new solutions and improving the known ones. So now we'll go back and open the Python code. So here is the Python code. We will go ahead and run it. Once we have run it, as you can see, the DTBO generation here also we generate or we iterate for 100 generations. So we also get the best parameter over here, that is 66 point that is 71.17 and 0.33, and then the best fitness, that is like 147. So, you know, to make to get a better understanding of what's happening, we can go back to our mini tab and then plot this graph out so that we can visualize what is happening. We'll open a new worksheet and then we will paste the values here. We will delete the unnecessary columns. We will name it as iteration. We'll delete the column which is not needed. We'll give this as a response, and then we will delete this as well. Now we'll go to graph, scatter plot, select this, okay, and then we'll go to response, select, and then iteration, select, and then we'll press OK. So once that is done, the graph is plotted. So now we can see that the DTBO rapidly converges to a highly optimized solution, reaching its best fitness at the 30th generation itself. And this method effectively balances the robot's speed with tilt control, ensuring smooth and efficient movement. The DTBO optimized parameters showed significant improvement in reducing the tilt angle and deviation. This means better handling under various load conditions, which is crucial for a cafeteria environment. Now, so finally, we have the ant colony optimization. For this experiment, what we did was we chose different coordinates on the map, and then we assigned those coordinates as tables where the robot needs to go and deliver its food, and we took that as a data set. Okay, so the ant colony optimization is inspired by the way ants find the shortest path to food. Ants leave the pheromone trails, that's the chemical that they leave behind, and over time the best path gets reinforced. So this algorithm mimics the behavior to find the most efficient solution. So how does ACO work? Again, you have initialization, you have path exploration, you have a pheromone update, and then you have decision making and then conversions. So initialization is ants start at some random point, okay, and then each ant finds a solution leaving behind pheromones. Okay, and then pheromone update, you have better solutions, get a stronger pheromone trails. So each ant like starts from a different position, and then it leaves behind a trail, and then like the thicker the trail, the thicker the chemical that is left behind, the more optimized the path is. And then decision making, which means future ants follow these trails which have like the prominent chemical content, and then convergence. So this algorithm, the algorithm eventually focuses on the optimal path. What we'll do is we will go ahead and we'll go back to Python, and we will run the code. So here, as I had said, that we have stored the uh, coordinates. So we'll just give the file. Once the file is given, we can see that there are around 100 iterations that have been done. And this is the path. So these were the coordinates that were given to the ant colony algorithm. So this was the optimized path that was found. So let's say we start at a given point, any given point, and then if we take this path or this uh, approach from one point to the other point, then that path will be our optimized path. That will be the least distance traveled. And we can see that the best path starts from 17 over here. We can see So the best path starts from the 17th point, and then 4, 10, 13, 6, 15, 8, and it goes on. And it reaches back to 17 because it's a closed loop. And the best distance that was found was 315 like centimeters. Uh, and these are the results. I mean, these are the iteration results that we got. We will go ahead and we'll plot this in mini tabs so that we'll be able to make like visual representation of these values. Again, we'll open a new worksheet. We will paste the values, the data points. We will, these are the iterations. Okay, this is a trash column, and these are the responses, or this is the distance. We will delete this, then we'll come to graph, then we'll plot scatter plot, and then okay. Our iterations, no, no, our distance is our y-axis, then our iterations, then select and then press OK. So once this is done, you can see the graph. So the ant colony optimization, it quickly found the shortest and the most efficient path for the robot stabilizing by like its 20th iteration. You have the longest chain. Okay, as you can see, it's around like 320 point something. So that is like most of the ants followed that until at the end, like around like after 80th, like, the ants found a better path. The difference is about like some 7 to 8 centimeters, because it's like here it says 315 and here it says 322, so that's like 7 centimeter difference. See, so at the end we came up to an optimal distance of 315, but still the best option was 322 because that is what the most number of ants followed. And this directly impacts that how quickly and accurately the robot can deliver food, because if it uses this optimization method and it has the set order points on the tables, it can quickly run the simulation and it can understand how I can go to what table at what order to most efficiently deliver the food. Optimizing path minimizes turning time and reduces deviation, ensuring that the robot moves swiftly and precisely through the cafeteria without unnecessary detours. So in summary, our study explored three advanced optimization algorithms to improve the performance of a cafeteria serving robot. Firstly, the genetic algorithm optimized speed and stability through evolution methods. Then driver training based optimization achieved rapid convergence by learning from iterative performance feedback, and ant colony optimization improved navigation by mimicking the behavior of the most efficient path. By combining these approaches, we create a robust framework that enhances the robot movement, reduces errors, and ensures stable, efficient service in real world cafeteria environments. Thank you for watching and stay tuned for more exciting tech insights.